No, no, nope, no. Okay. Hi everyone. Welcome to the tutorial I promised everyone I would put together for basically going over the same we did in class, but now in a video form, having a tutorial of the LeSerre third floor ARCHSIM example. And I'm making this tutorial while babysitting the little one. And you'll see this tutorial goes back in time. If you guess a timestamp at the bottom right of your screen, it says it's 5 p.m. on Sunday. Well, this tutorial started sometime Saturday afternoon, and in different parts we ended up to right now where we finished. Come back. This tutorial, what we're going to go over is to get to the end point of what you see on your screen now, which is a pie chart showing a breakdown of annual energy use in terms of lighting, electric heating, and ideal heating, which we will use ARCHSIM to calculate for us for the third floor of LeSerre. That tutorial, of course, starts here. Yeah, it starts here with the LeSerre third floor Rhino geometry. Which is a geometry file, as well as some other files that are on UBC Connect. With all of that said, we're now going to go back in time about just over 24 hours where Olivia was more cooperative to the start of this tutorial. Enjoy. So we're going to start with looking at the Rhino geometry file for the third floor of LeSerre. This is the geometry file we built our tutorial off of in lecture, and of course it's a good start in comparison to what you're asked for assignment 1. This geometry, as I've created it, has 3 layers, and I should mention that the layers, it's not mandatory, or there's no for ARCHSIM requirement that you have these 3 layers as they are written, and you can in fact do your whole geometry in 1 layer. But it helps me when I'm making these simulations to have 3 layers to define my geometry. And I'm going to turn off the glazing and shading geometry so you know and you can see what is the starting point. And this is the kind of starting rule for any ARCHSIM geometry. Your form and what you'd like to use to simulate the energy consumption, whether it's a single room or in this case an entire floor, must be represented by one solid joined block, not a collection of surfaces, but really a joined body in Rhino terminology. You'll notice that this body, which is the same proportions as the entire third floor of LeSerre, has no windows associated with it. It has, of course, no interior floor plan. It may have a collection of surfaces on the outside, but really it's just an extruded rectangle for LeSerre, which is good enough, and it's a simple geometry to start with. I've put that on the default layer, and again, I could call this body or I could call this building, but the point is to have your building form in one body, simple body. Some of you may already have ideas of having curved surfaces or perhaps curved roof structures. I think, as far as I understand it, and that's maybe a discussion for another day, provided that you have hard edges between the vertical and what are more or less horizontal surfaces, I think provided you have vertical surfaces defining the exterior wall, it will assume that everything that is connecting the vertical at the top edge and anything connecting the vertical at the bottom edge is their floor and roof respectively. That's my understanding, and I may be wrong, but in this tutorial we're not going to go beyond a very simple form like this. So we have our body as discussed, and if I were to click on the glazing layer, you'll see these blue surfaces appear along the outer walls of the body and the kind of building geometry under the default layer. Now, these are surfaces as compared to default being a body. So if I hide the actual body of LeSerre and turn off the default layer, you'll see that these are independent surfaces that are created, that I've created to represent the windows of LeSerre. It's important that these surfaces are overlaid onto the wall surfaces. So if you have some errors and you've actually placed these window surfaces that they're physically disconnected spatially from where they are on the body, ARCHSIM won't actually directly associate them as windows. So you want to make sure that these window surfaces are overlaid onto the appropriate location on the building body, but just have them as different layers. Last is this magenta layer I've created called shading. And recall that in the shading surface, or these surfaces, they can be any type of solid solid shape. They can be surfaces, they can be bodies, they can be round, they can be square, they can be whatever. ARCHSIM interprets everything on a shading surface or a shading layer to represent external obstructions such as external shading elements or other buildings, vegetation that are used by ARCHSIM to understand where there are intersections between the building form and the sun. So the main point is these surfaces, whether you have them as bodies or not, are used by ARCHSIM to understand where there are obstructions between the position of the sun and the built environment. And that obviously can reflect shading as much as it's obstructions, and the whole point is to give you a more accurate understanding of the effect of external obstructions on solar energy interactions with the building. I've only estimated obstructions for LeSerre, and for those of you working on assignment 1, I highly recommend you do not use these obstructions. These are examples. If you want to be accurate with your 4th floor simulation of LeSerre's 4th floor, there you want to get from your own research and understanding of what obstructions may actually be there that exist on the 4th floor geometry. Again, it's not important that you call this layer shading. That comes later, but by convention, I like to have all of the external shading elements on their own independent layer called shading. Apart from that, that's it for the geometry. Again, for a single floor study, we keep it very simple. We don't have any interior walls, just a standard block for the building form. Simple surfaces for glazing, and then any type of forms you are interested in for representing shading elements. When we're ready, we can open up Grasshopper. In this case, I have a little error with my Grasshopper. We just click that. Okay. So we'll start a new document in Grasshopper, and we'll go through some bits of the workflow of creating an ARCHSIM model from scratch. But at some point here, I'm actually going to switch to the kind of standard tutorial Grasshopper file that I've created previously and which I provided for you on UBC Connect. And clearly, Olivia is enjoying this entire tutorial. So when we start, my Grasshopper is filled with a bunch of stuff you may not have, ladybug, honeybee, firefly, etc. But really, the tab that you want to be concerned with today is, hopefully, if you have it installed correctly, this ARCHSIM tab. And that will have, for the most part, all of the tools and techniques we're going to be calling on today. The starting point, if you remember, with an ARCHSIM simulations, we need to bring in our Rhino form into the Grasshopper domain. So all of these processes that we're going to undertake in Grasshopper, they actually know which geometry we're referring to. And we do that with these ARCHSIM components, and we treat, and this goes back to why I've represented the body, glazing, and shading as different layers, is because in ARCHSIM we also treat these as 3 independent components when we're assembling our ARCHSIM model. In ARCHSIM you'll see this thermal model tag, and we have several components here. I'm going to start by bringing in the thermal zone, which represents really the building body. It's the walls, or facade, the roof, ceiling, and floor. This block has 3 inputs: a vrep, a name, and a set. And in order to connect this thermal zone with the building body, I'm going to double-click just to the left of this thing, and I'm going to say vrep. And you'll see this component on pull down this list menu showing an icon here for a component called a brep, and I'm going to click on that. And that's a component in Grasshopper that allows us to link Grasshopper, what's happening in Grasshopper, to a geometry that we've created in Rhino. When that's in the canvas, I'm going to right-click on this brep icon, and you'll have a lot of options. And the option I'm interested in is Set One brep, which will ask me to pick one shape, whether it's a body or a surface in Rhino, to associate with this brep. So I'm going to click Set One brep. And when I do it, it will automatically send me back to the Rhino space. And the intent here is to click on what you think is the body brep that you want to bring into Grasshopper. And in this case, it's the actual gray default building body, building form. Click on that, and right away, it brings you back into Grasshopper. And in order to see kind of better show what's happening, I'm going to move my Grasshopper screen to the right here. Rearrange my screens, and I'm going to do the same with Rhino. Okay, so here in my case, I've now separated my screen to having Grasshopper on the right and Rhino on the left. So I'm now, this is after I've selected the geometry, and you'll notice that if I click and select the brep in Grasshopper, you'll see that the body of the Lacer's third floor has been highlighted in green, and if I click away, it not highlights. And I like this as kind of usually an easy check between whether I've selected the right body or not, or surface or not. So when you're satisfied with having linked this brep to the body of the building, connect that input to a brep. I'll zoom in here so you see what I've done. So I click and drag here to brep, and the connection is made. If I make a mistake and I want to delete this link, I click on the starting point, then I hold Control, and you see if I hold Control, we get this negative red, which is a delete symbol, and then I delete that line. And if I then make it normally, I can recreate it. So if you want to delete a line, my technique is at least start from the starting point, then hit Control, and you can delete that link. Anyways, we start from there as a brep name. It's useful to give a name to this work because this whole ARCHSIM process saves files onto your computer, and those files will have a prefix that is a name that you associate to the simulation. And the way it makes sense at this stage that we'd want to think about giving a name to this zone, which also will associate itself as a name for the simulation. And why a name may be important is when we run ARCHSIM, in the background it actually creates a number of files on our computer, and those files will have a prefix, and that prefix is often associated with the name that you give to the geometry and the simulation files as you assemble this ARCHSIM model. So we'll create a name, and I'm going to bring in the arbitrary text box that you use in Grasshopper if you want to assign a text input or a number to any component you may be working with, and that's a panel. So I double click inside the space where I'd like to add a panel, and I pick a panel from that menu, and it'll tell you what you see here. Double click to edit the panel content, which I do, and I'll just call this Lacer third floor. I use underscore in lieu of spaces, so I try not to have any spaces in this naming, because especially if it's going to be creating files on a computer, usually Windows doesn't really like to create files that have spaces in the name. So when I have a name that I'm happy with, you can call it what you like. I connect that to the name bracket of the zone. That's all we're going to do right now. We don't ever really have to worry about these set terms, at least for what we're going to be doing. And there's some other things when we have to set with the zone, but we'll do that in a little while. So that's the building zone. We'll do now the same associations for a window element. So we will bring in, that's actually a shading surface that we're bringing in. and window element, which is in fact this. Sorry, I think I'm hiding it from my services. We're now going to follow a similar approach to what we've done for the last few minutes to add the window and shading layer to the grasshopper space. We're going to bring in the window component, which is in this thermal mode, thermal model category, and a shading surface just to the left of it here as a block just below. And the window, as we had for the building zone, has this BREP input. In shading, they call it surface, but it can also, in the situation here, be associated with a BREP, just like the window of the building zone. So I'm going to create for the windows a BREP to associate Rhino geometry to Grasshopper, which is right here. And when I right-click on it this time, as opposed to setting one BREP. In this case, because I had actually multiple surfaces for glazing, we have a north glazing on the north facade, on the south facade, east and west. I'm going to click Set Multiple BREPs. And when I get back into Rhino to select these surfaces, I'm going to use Shift to select multiple surfaces. You'll notice as I go around the building, I'll have a total of 4 for all of the window surfaces I've created shown. So when I'm satisfied and I've picked all the BREPs I want to associate with this one Grasshopper component I've created, which are all the windows, I then hit Enter to return to Grasshopper. And just before, when I highlighted this BREP and I saw the body turning green, if I highlight this new BREP I created, you'll see all of the window surfaces have highlighted in green, which tells me we've done a good job. I then associate that BREP with the input condition of the window. At this point, you probably know where we're heading with the shading surfaces. Again, I create a BREP, and I'll set multiple BREPs for this component, and I'll highlight the shading elements as entire bodies, although I could just pick surfaces if I'd like. Good, and when I'm done, I head back to Grasshopper, and if I if I click on this BREP, I can note that my shading elements are highlighted in green, great. My windows, again, backtracking, and then my body. So we're all set with our geometry, and we connect that BREP to the input surfaces of the shading element. Great, that's now our independent geometries brought into Grasshopper in the format that ARCHSIM likes for representing the building body, windows, and shading. Now we need to get ARCHSIM to understand that all of these three interact together as one building form. And we do that by bringing in this component. You'll note here at the top right, Zone Connectivity Network, which really connects all of these systems together to create a single combined thermal zone with windows, walls, ceilings, and shades. When you're ready with that, you'll see that this model, as you bring it into the space, has inputs zone, windows. If you highlight this BCO, it speaks of boundary conditions. We will ignore that today. It has a shading input, which we will use today, and then a library component, which we will ignore today. So for the zone, windows, and shadings, you can maybe guess what we'll likely do in the Grasshopper using the kind of the format we've been using so far. We connect zone to zone, window to window, and shade to shade. And with that connection, we now have created a single model that understands that the building geometry, the windows, and the shading systems all really are communicating with each other as one, and are really altogether one representation of the built environment. This model now represents an ARCHSIM geometry model, and these settings, which we'll get to in a few minutes, will speak about the conditions of building fabric, occupancy, the quality of glazing, etc. But for the energy simulation calculation, we need to bring in the actual calculator that does the number crunching and predicts the energy consumption for us, which is Energy Plus, this physics-based energy simulation model that does a kind of a deep hourly or every 15 minutes, in this case, simulation of energy consumption based on geometry and site climate. So we take this Energy Plus model and we bring it into the space right next to our model. And it has quite a number of inputs. We'll go through them, but intuitively you may guess what we'll probably make as the first connection, which is the model output of a zone connectivity network to the model input of the Energy Plus model. As far as a name goes, we could create a new name, but if you want to save yourself some time, and if it's all the same to you, you can actually drag a second point from this original Lasserre third floor name we created to the input name of Energy Plus. So here we're not only just calling our geometry Lasserre third floor, we're also calling this Energy Plus model Lasserre third floor. You can change that. It's totally up to you if you want to have different names. It doesn't change anything directly. One thing I should point out that's different from what I understand is an issue with those of you who download the Grasshopper file that's on UBC Connect is this directory file should show you what the video is showing you right now, which is actually a directory on my computer. And I think when you use this Grasshopper file on your computer, it still thinks it's my computer, which will likely give you an error because you don't have likely C users Ryzen desktop. So I would recommend, this is where an area where you may want to create a panel. And you may want to create on your computer my ARCHSIM folder, or call it what you would like, and maybe use that as a working folder for the Energy Plus simulation. This input is telling Grasshopper and the Energy Plus simulation of Grasshopper where should it actually store and access files for the simulation. And obviously this should be a folder that actually exists on your computer. And you'll notice that if now that I've created that panel with that text, this dir tag is no longer, directory tag is no longer showing users at Ryzen desktop. It's now actually showing a folder on your computer, hopefully. So replaces my ARCHSIM folder with the location of any actual folder, and you may create this yourself, the folder that you want to use these files in. As we continue down, the next step is this EPW pull-down menu, which is related to the actual climate file. And this pull-down menu will likely show you all of the climate files that come installed by default with ARCHSIM, which are primarily American cities, the closest one to Vancouver being Seattle, and there are definitely no, with the exception of Anchorage, no real city that may embody something like Yellowknife Northwest Territories. So you need to concern yourself with installing likely a climate file if your site climate has nothing to do with these locations. So I'm going to run through the process of quickly installing a new Energy Plus weather file if I don't see the weather I like here. I could, for this case and for your assignment on my computer, I have Vancouver. You may have to install it. I'm going to test this workflow by installing a weather file for Ottawa in Ontario. So I open up Google and I search for Energy Plus weather files. And you should get a link to this website, normally the top hit on your search, energyplus.net/weather. Some of you will remember this process from ESAC 1. and I'm going to navigate to North and Central America, Canada, Ontario, and I'm going to find Ottawa, and I'm going to download all. This opens a zip file into this computer's downloads directory. You can choose to download it wherever, but the main point is you want to extract the zip file, and when you do so, 3 files should emerge from the contents of the zip file. A file which has some coding in ottawa.epw.stat.ddy. I'm going to copy all these files. Try to do easily with Control-C, and then I'm going to navigate to my Diva install folder, C, Diva, weather data, and then here is where I have all of the weather data installed by default, including one I previously installed from Vancouver, and I'm going to paste those 3 files here. And that's really all you have to do to install a weather file. So the main point is to install these files, EPW stat.ddy into weather data. A question was raised whether it needs to be all 3, whether you can't just find an EPW file. That may be possible. I haven't tested that, but I tend to install all 3 files that we can find online. After doing so, if you go back to Grasshopper and click on the EPW list, you should now see this new city added, and now we see Ottawa here added to the list, and I'm going to click on Ottawa, and that automatically sets the whole simulation to use the Ottawa climate data, which is used for outdoor weather conditions, including solar radiation and the position of the sun. That's all we need to set up the kind of the flow of the simulation. And the only last bit you would want to run if you kind of create this on your own is some trigger to tell Energy Plus to actually execute the entire simulation. There is this run tag here, which is what we want to trigger and turn into a value of true to run the simulation, but it needs some help to do so. And we do that by adding a button, which if I double click inside the Grasshopper space, and I type button, I'll have this option here, a button object with 2 values. And that's a mouse click button that you can see if I click it kind of changes its value to, well, you won't be able to see the value, but if I click it, it changes a value to true. And I associate that with run such that when I click on this button, it will actually run the Energy Plus simulation. From this point onward, you would have to start going through the settings of individual zones, setting the construction materials, whether there's air conditioning, ventilation, etc. But I'm going to stop there with this file in terms of the file that we've created on our own. I'm going to now skip a few steps and open up the Grasshopper file that I gave to you on UBC Connect and that we worked on in class. So if you open up that Grasshopper file, it should look roughly like what we've just created. It's in fact linking to the same geometry file. So we have a geometry input for our body, our windows, our shading, which are now disabled. We have an Energy Plus tag, which is running the Energy Plus model. And in fact, there's 2 of them, which I'll explain shortly. And then the psychrometric chart, which is an optional component, a set of components I've added that plots a psychrometric chart inside the Rhino space of the results of the simulation data. The reason why we have 2 Energy Plus, kind of almost duplicates of the Energy Plus module, is related to the settings, and we might as well go through the whole process of settings now, and then we'll explain this hourly, monthly in a bit. So we have 3 settings we need to concern ourselves with before we run any simulation of a building's energy consumption. And the 2 main ones are the settings related to the building geometry and occupancy patterns and whether there's heating and cooling loads, etc. And the same we need to do for the windows and setting the kind of parameters for the R values for the window, shading, etc. And we'll start this process by first clicking on the settings box or tag that's right underneath our zone component here. And you'll see there are 5 tabs open: loads, conditioning, ventilation, hot water, and constructions. And all of these are configurable, and they can be configured in a quite detailed manner. And to some extent, the options you have available here go beyond what you may want to approach just for your investigations in ESAC 2. The ones I would recommend that you concern yourself with are the obvious ones, which are on loads with respect to specifying whether there are or are not people inside your simulated space, and roughly what type of a schedule they fit to. In this case, for LeSerre 3rd floor, we can use the built-in schedules they assume for office occupants, as well as specify a density, people per square meter. And you will have to guess for your assignment what, and some of you have done this previously last term, what are a rough number of people per square meter for your simulation zone. You have to do the same for equipment in terms of the power density of equipment in watts per square meter. There again, some guides were given to you in the instantaneous energy calculator, which I will have online for those of you who haven't used it before in ESAC 1. The same goes for lighting, where you not only need to specify a power density for lighting in watts per square meter, but also a target lux, which often has to do with the programming of a space. Offices, for example, tend to have either regulated or target indoor light levels between 300 and 500 lux. Residences and other types of spaces may have lower lux targets, and others may have more. Whether your lights are dimmable or not is an option to you, and of course so is the light schedule. You have to specify these parameters as close as possible to what you think are target values. I'm going to leave conditioning to the last because that's maybe the more complex one, and I'll go right to constructions. If you remember in our class, I spent a bit of time talking about what this term means, adiabatic or not. And for the record, I should give it to you again here. In this list, here's where you specify the physical properties of the facade in terms of kind of materiality of it, whether it is a 200 millimeter concrete wall or it's a thinner wall with insulation, etc. And ARCHSIM gives you some options for different types of constructions. You can have, for in this case for the roof, a 120 millimeter insulated roof with 200 millimeters concrete, or 200 millimeter concrete roof, or 115, etc. You should use, if you have them available to you, existing construction documents to gauge what are the likely or closest material constructions to what you're intending to have built. Or vice versa, you may want to use these as different design options if you're trying to find the optimum or the best constructions for either passive design criteria or winter passive design or summer passive design. ARCHSIM makes available what are called default constructions, which are just arbitrary values of insulation and material thickness, of which are somewhat indeterminate, at least indeterminate from our point of view as a user. And I recommend only using them when you have this association, as an adiabatic surface. An adiabatic surface, in the context of this simulation, represents any surface that has no heat transfer involved with it. And we want to represent surfaces that may be connected to other floors where the temperature of the other floor would likely indicate there's actually no heat transfer in between the two floors. An example of that is LeSerre's, in fact, perfect example of that, where between the 3rd and the 4th floor, during the winter time, we don't expect that much heat transfer to occur between the two floors because both floors are actually kept at the same temperature by LeSerre's heating system. At least ideally they are. So we call the boundary between the 3rd and the 4th floor in LeSerre adiabatic. The last box we'll concern ourselves with on this screen is specifying values for the internal mass. And the definition of the internal mass in this situation and they call it exposed surface area. This is to describe the kind of net surface area of things like internal walls and almost a kind of an assumption of if all the furniture and every physical object within the zone was made out of this construction material here, which you can select out of your pull-down menu, roughly what would be the net exposed surface area of that equivalent thermal mass, which can be very hairy for anyone, including the most expert engineers, to estimate. So this tends to be a difficult value to specify, and a rule of thumb would be at least to think about not necessarily the furniture, but at least the internal walls, and estimate a net surface area of all the internal walls inside your zone, and assign an approximate construction that may reflect the thermal mass of those internal walls. If you know that your internal walls are made out of solid wood with gypsum board or particle board on either side, then great. If you don't know, you may want to assume that it's a heavy construction like concrete. This value, what you specify here, can do a lot to affect not only the accuracy, but just kind of the variety of results you get from the simulation model. So you may want to be conservative here with with internal mass and pick as small a value as you think is appropriate. Not too small to be impossible or unrealistic, but perhaps your most conservative guess for the value of internal mass. Beyond that, this tag about zone behavior, I wouldn't recommend changing anything here except for maybe the roof tilt angle, which depending on the actual angle of the roof of what you're designing for, you may want to specify a value here, but that's about it. I wouldn't change things like these algorithm tags or order, priority, etc. We'll move on to ventilation. Here, if you wanted to, you could specify conditions of mechanical and natural ventilation. And you absolutely can go as far as really doing detailed mechanical ventilation system simulation, if you will, within ARCHSIM. But for our work and for this initial tutorial, I wouldn't recommend doing so. What I would recommend is if you have openable windows to concern yourself with, I would turn on natural ventilation and turn on buoyancy-driven flow and wind-driven flow. And I wouldn't worry too much about schedules and temperatures here, with the exception of verifying that your set point temperature, which is the temperature that people would be trying to control the windows for, is appropriate. In this case, what this means by having a value of 24 means to say that in the summertime, people are likely to be opening and closing the windows in order to generally get to a temperature of 24 degrees indoors. And that maybe is not a bad choice for LeSerre. Thank you. Then last one on this window is infiltration. And of course, infiltration is an important concern in predicting the net energy consumption for buildings, so we for sure would like to keep that on. You can choose whether this value is constant or use an algorithm within ARCHSIM that actually calculates a fluctuating value that's related to the actual wind, which isn't a bad idea. But you need to give some mean average value as a guide. And some of you who've done a model of LeSerre in ESAC 1 may already have a value in mind here. And those of you can certainly Google online or see some documentation on UBC Connect that will give you guidance on what kind of value you may want to specify for a building like LeSerre. When it comes to conditioning, without any discussion, I would ignore, right for the moment, mechanical ventilation and humidity control, and just concern yourself with cooling and heating. If you click heating and turn it on, this is indicating to ARCHSIM that it will create an ideal heating system that has no real componentry. It doesn't have a boiler, it doesn't have ductwork, it doesn't have anything. It's just a kind of a theoretical heating system that will calculate the fundamental amount of energy required to heat up our Lasserre case to a set point temperature we specify over a certain schedule we specify. So in this case, we have a occupant office schedule, which is should be a kind of a 9 to 5 weekly schedule, and a set point of 18 degrees. So we're telling ARCHSIM that, oh, thank you, Olivia. We'll take that back down to 18. We're telling ARCHSIM that we would like to simulate a heating system that's trying to heat Lasserre, the third floor of Lasserre, to 18 degrees weekly from, I guess, 8 to 6 or 9 to 5. If you set no limit, which I would recommend, it ignores these next two boxes, heating limit and flow limit, which we won't explain. So if you keep to no limit, then really you only need to worry about the set point and the schedule. And if you have a cooling system and your desire to have a real active space cooling system, you can do the same for the set point and the schedule. And I will leave to you whether you think it's appropriate or not to do this for Lasserre. That's basically it for this screen in setting properties. Last, in this case, we want to set the window properties, and here, although there's a lot of options, we only want to worry about a shading system and the window and the construction. So the pull-down menu for glazing construction speaks mainly to the resistance value and how much light is allowed through the window, whether it's a single pane of glass or double glazing. A window frame speaks to thermal bridging and kind of estimates the amount of heat loss that is attributed just to the frame alone. And you may want to find an appropriate resistance value or U value for the frame conductance and a width of the frame, or just leave it to a standard value as shown here. And if there is a shading system like interior shades, and they adhere to some form of occupancy schedule, you may want to turn on and off the shading system and maybe give it a default treatment like it is here, or personalize these values somewhat. I wouldn't recommend changing anything about the natural ventilation settings. This links to whether you have natural ventilation or not, and you can leave everything here standard. So I would, long story short, parameterize this as appropriately you see fit. Probably the most important thing for you to worry about is that you have the right window selected, that you've specified an appropriate width of the window frame, and you've determined whether or not shading or internal shading or exterior shading is at play. Finally, we're getting towards the end of our need to configure this, and the only other ones we want to configure, although you may not need to do this configuration, but I will run you through these settings of the Energy Plus modules. So if I click on the Energy Plus settings module, I'll get this screen where it's, in fact, allowing you to configure the Energy Plus simulation, whether you want to run an annual simulation or maybe only want to run 1 month, which you would specify here in the run period. In this case, we're running a full year. And most importantly, and this speaks to why we have a duplicate of this, is to specify the resolution of your outputs, the data that the whole process is generating for you, whether you want the resolution to be hourly data or monthly data. And that's why I have now 2 duplicates of this. I in fact have a simulation box that generates hourly data and the other one that generates monthly data. You can look at the hourly one on your own time. Let's look, because we're concerned in our case about the monthly data, let's look at just the monthly data for now. If I click on the settings for the monthly data, you'll see that the resolution is monthly, and the other one was hourly. And the output variables are actually the variables out of a long list, the select number of variables that I actually want to output to a data file that we'll be using later to plot some results from. And if you go through this file, you'll see there's not that much selected. We have Electric energy, which is useful for us to know how much is ARCHSIM estimating, will be the total electric energy required for lighting. The same for the total electric energy required for electrical appliances indoors. And then the only other ones, and it's important because there's a lot of different ones that are very similar. Here I select zone ideal loads total heating energy and zone ideal loads total cooling energy. There are also some tags that sound very similar, like a zone ideal loads outdoor air sensible heating energy or outdoor air total heating energy. Then there's also some supply air total heating energy. Those other keys speak to whether or not you are simulating a more complex air conditioning system. If you are, as we're trying to do here, trying to just simulate the kind of basic theoretical amount of heat that we need to provide to this LaSerre third floor case or not, the outputs we want to generate are the ones already selected. Zone ideal loads, zone total heating energy, zone ideal loads, zone total cooling energy. And lastly, I have water use equipment, which we won't go through today, but I put that in there, and it may in fact become a useful output for you at some point in the course. So really, for this, for all of these options that you could output, we're only actually looking to output the kind of key categories of energy consumption: lighting, appliances, heating, and cooling. And when I'm done, I click OK. Obviously, for this simulation, this file, I'm using my default directory, and I'm using the Vancouver, well, I'll select it now, Vancouver weather file. Again, you're going to want to verify these as we discussed early in this tutorial. At last, we have a simulation that's ready to simulate. And all you have to do when you're ready to go and you have this button set is to click on this button. And you'll see this text box open. This is ARCHSIM really running a simulation. In my case, it actually only takes about 5 seconds on my computer. It may take you a little bit longer, but I wouldn't be surprised if it's relatively quick. When the simulation finishes, in the folder that the Energy Plus module is configured on, in this case it's the desktop on my computer, will be several new files created. And if I go to the desktop and I sort by date modified, see the time right now is just after 4 o'clock, and you'll notice that I have just around 4:11 a bunch of files that were just created, including this LaSerre third floor _ monthly out, which is the same name as my monthly simulation, LaSerre third floor _ monthly, and the only addition is this suffix out that was added. And if I double click on this file, I now have, and if I'll wrap text this, I now have a very simple text file in Excel that has, for every month, electrical energy monthly, equipment electric energy monthly, zone ideal loads for heating, and zone total ideal loads for cooling. Now, because I've specified my default model in a way that's not accurate for LaSerre, these numbers are a bit funky, say for heating. You'll notice that I have heating between May and October, but not elsewhere, which is certainly odd. But I expect you, with the inputs that you specify for LaSerre, to find a value to have values that are more realistic. Now, these values are huge. They're in joules because 1 joule is in fact a very small quantity of energy. And we often like to speak of in measuring energy consumption per month, usually in kilowatt hours. And I'll just create a duplicate of every column here. I'll do electric lighting energy in kilowatt hours, electric energy of electric appliances in kilowatt hours, ideal heating in kilowatt hours and ideal cooling in kilowatt hours. And the conversion is I'm going to just convert all of these values, and the conversion, I'm going to go quick because hopefully we've done this enough, that a conversion between lighting energy from joules to kilowatt hours is divided by 3600, which adds the time component, the hours to the numerator, and then divide by another 1000 to go from joules to kilojoules per second hour. All that fun math stuff. Long story short, from joules to kilowatt hours, you divide by both 3600 and 1000. So in fact 3.6 million. And that gives us a value that's smaller. It may not mean much to us now, but as we start comparing the energy consumption that's predicted here to benchmarks, you'll often find the benchmark values online, like for instance government benchmarks, in units of kilowatt hours per month or per year. Last, if I want to get an annual value, then I just have to add up the estimated value of every month. And here now I get the total values for lighting, electric appliances, ideal heating, and ideal cooling for every month of the year. Now I haven't normalized these to floor area, which means I haven't specified these in kilowatt hours per square meter per year. This is total kilowatt hours per year. Your assignment will ask you to do an extra division, which you'll have to think about. But if in Excel I just wanted to make a simple plot of this value, I would just have to highlight this collection of cells, the annual and the categories and the values, have a pie chart, and now I have actually a pie chart that shows me, at least in this case, the heating load is very low compared to appliances and lighting energy. But your simulation may show you something different. Now, this graph, as it is right now, looks a bit funky and unclear. I'm also showing that I'm trying to plot ideal cooling that really has low value because we're not actually simulating cooling in this case, or have no cooling loads. So I'm going to just clean this up quickly, and you can find, whether you like Excel or another tool, you can generate these pie charts in Illustrator if you want to work on kind of raw design of these charts, or find another tool that works with you. But in my case, I'm just going to quickly work on some formatting, and you can follow along if you see what I'm working on here. So now I have a pie chart based on ARCHSIM data that estimates the breakdown of ideal heating requirements, electrical appliance requirements, and lighting energy requirements. Together, that's the starting point for knowing what is the typical expected energy consumption of this building, and we can compare that to target codes and standards. We can also use these results plus available data on solar energy resources and renewable energy resources to know whether our demand can fit available supply. We can in fact do quite a lot just with the monthly data and even more with the hourly data, which we haven't gotten into. For now, we'll leave the tutorial there and see how far you can go along into generating for, in this initial case, the ESAC 2 first assignment for the fourth floor of Le Serre. And from there, we may work together again in the class on how to evolve an ARCHSIM model further for your studio work like the Comprehensive Studio this year. Hopefully, this is easy to follow, and of course, I'm always around for questions. You haven't heard Olivia for a while because she's napping, and that's always a good thing. Have a good week.